make it probably hard to go to the cafeteria today. But yeah, I will try. So the topic of my talk is the generalized omega background and the holomorphic anomaly equation, and I start, so to say, with a formal definition of the omega deformation of omega deformation. So this is very formal. It just tell you how so what we used to see as the topological string partition function is actually deformed. So this would be the following deformation that I consider. So I have two parameters, epsilon 1, epsilon 2, and correspondingly I have two integers, and they give a generating function which is organized in this form. So you see, G should remind you of the genus, and K is another integer, and then you have functions which are indexed by these two integers and which depend on the Kähler parameter. So this would be the Kähler parameter of the A model. And of course, the first thing that you ask, what has this to do with the usual definition? And then there are, in fact, limits. And the most important limit for this talk is that you set epsilon 1 equal minus epsilon 2 equal I GS, where GS is the string coupling. And if you do so, then you just get back the normal topological string partition function, or free energy if it's a logarithm of Z, which then, where GS just counts for the genus, so it's 2G minus 2, and so here is actually G minus 1, and then it's F 0G of T, and if you take this F0 if you consider what this function is, F0G of T, then it's basically the Gromov-Witten invariance G. So it's a sum of a beta in H 2xz, where X is the Calabi-Yau background, and then this is a generating function for these ones, where E is basically e to the 2 pi I tau, and then you well, this is basically the degree of the degree of the curve that you're considering, and then this is the normal Gromov-Witten invariant. So R G beta is usually an element in Q and is the Gromov-Witten invariant of this Calabi-Yau threefold. So that's the context that we are talking about this. And so in some sense, it's so it's a generalization of the Gromov-Witten, or it's a generalization of this expansion, and this is the first limit. The second limit, I don't talk too much about it. If you set epsilon equals 0, and then epsilon 2 equal h bar non equal 0, that is the so-called Nekrasov-Shatashvili limit, and it's also very interesting because in this limit you get a quantum integrable system. Leads to a quantum that is known. But for us, it's more interesting to see what is the refined information that is in this, what is in this expansion. So I try to give a definition of the well, I mean, in some sense, well, the point is the definition of the generalized Gromov-Witten invariance is a challenge, so I don't know how to do it. But there is a physical definition of generalized BPS invariance, but we have at least a physical definition of generalized BPS numbers. And this I want to give you a little bit. So what is the setup? So you you have n equal to supersymmetric series in 5 dimensions. And one way to do this is to consider M series. I mean, there are different ways of doing that, but one way to do it is consider M series. Then there will be a relation to the Calabi-Yau. So you consider M series on a Calabi-Yau. So we have on X, this is the Calabi-Yau threefold. And then you compactify this further on an S1 times R4. So this is the this gives the supersymmetric series in 5 dimensions, and then you compactify this further on this space. So this is the 5-dimensional space on which the supersymmetric series lives. And now you can worry about the symmetries of the series, and there is of course SO4 rotating R4, and you can it's more convenient to denote this by 2 SU2s plus and minus, which are essentially the same than this one. And then we have the Cartan subalgebra and U1, or the Cartan subgroup, U1 plus times U2 minus. And we actually call the rotations in this group epsilon plus and epsilon minus, where epsilon plus minus is just 1/2 epsilon 1 plus minus epsilon 2. Now, in such a situation where you have supersymmetry, and how do I get the other up? I cannot, it's fixed. Yeah, okay, then it's simple. But it's unfortunate, of course, because you cannot see it. So I should have started the other way. So the so now you can actually take this R5 fibered over the S1, so you make a non-trivial fibration, which is twisted. So we consider a fibration which is twisted. So if you go around this S1, you also make a full rotation in the 2 U1s by U1 plus times U1 minus. And now you can, if you have a supersymmetric series, you can define an index. And in some sense, since the U1s are central elements, you could find a refined index which also measures the charge of the states with respect to these U1s. And that does not work immediately, because if you rotate with both U1s independently, you break supersymmetry. So we need actually the fact that the 5-dimensional series has an additional U1R symmetry. So this is symmetry which rotates the supersymmetry generators, and it has this if X has an U1 isometry. And only if you have this additional U1, you can form a combination which preserves supersymmetry. So, so under these circumstances, we can find combinations. This is J minus, which generates this U1 minus, and then J plus 3, which is a combination of this, what I've before called J3 plus the generator of this U1R. Actually, this sits always also in an SU2R, so it makes sense to call this J3R. And so this symmetry is preserved supersymmetry. Preserves n equal to supersymmetry. And then you can define an index, so we can define an index. So this index is now what I would call epsilon 1, epsilon 2, or plus or minus, doesn't matter. So this is the same quantity that I had before, now written as a supersymmetric index. It's a trace over the Hilbert space of this 5-dimensional theory, and you can you have a minus 1, 2 m plus m minus, where m plus minus is the highest eigenvector, the highest eigenvalue of the SU2 plus and minus representation that you consider. And the and then you can, so to say, trace this this eigenvalue in the partition function, and then you get Q beta as before. So this is a physical definition in terms of BPS states of what I mean, the degeneracy of these BPS states are actually the refined information that is in this refined partition function. And so this is defined, and it can be actually expanded. So it is useful to expand Z epsilon plus epsilon minus as follows. So so we take we take the log of Z, and then we write it as a sum, and the sum goes now over beta k equal 1 to infinity, and then it goes over this j plus minus from 1 to infinity, and then here is the product over plus as well as minus, and then it's a sum m plus minus equal j minus j plus minus to plus j plus minus, and then q plus 2m, so is 2km plus minus. So this product is over both. And then you get the things that we are really interested in. So this would be G plus, G minus. And these are actually the most convenient definition of the BPS number. So they are in Z. These are the BPS numbers that, that you want to define. And then this is written here in this following way: k sinus hyperbolicus k epsilon 1 half sinus hyperbolicus k epsilon 2 over 2. So this is the is the definition of the extraction of integers once you have this index. And this one, of course, now you can ask yourself what happens if you make contact with the topological string again. So so if epsilon 1 equal minus epsilon 2 equal IGS, that means that epsilon plus is actually 0. And what happens is that you get, of course, an index which over the m plus is now just summed. So you only get numbers where over the m plus is summed. So you can write this as, or over the j plus is summed, j plus 3. You can write it as this. So you get, no, let's call this m plus. So you get a sum over this m plus to m plus plus 1. And then you get the n m plus m minus. And then you get the representation m minus. And this can be reorganized in this form, like n g beta, and then 1/2 of the minus representation plus 2, and then the trivial representation in the minus representation to g. Sorry, to g. So this actually defines these numbers in terms of these numbers, and you see what you lost is the information of the plus spin, and these numbers here are, of course, just the. So these numbers are also integers. So it's like an index of these. I mean, it's like a weighted sum of these finer indices here, and these numbers are precisely the ones that are now completely equivalent. So this information, the information is 1-to-1 between these ones, and these ones were actually used by Pandya and Thomas. So these are the later related by Pandya and Thomas. To invariance of sheaves. And in some sense, this maybe is the closest thing that we get to a geometric interpretation. Now, if you include the right spin, that should be a finer invariance of sheaves, and that is something maybe that can actually be defined.
We have a lot of questions about notations.
Yes?
First of all, epsilon 1, epsilon 2, how do they relate to epsilon plus minus?
Epsilon, this should have been given in the blackboard before, but it was like just epsilon plus minus is 1/2 epsilon 1 plus minus epsilon 2.
Okay, but q plus minus, how do they relate to epsilon?
Yeah, so then this is fairly obvious. So q plus minus is e to the epsilon plus minus, so that this thing depends now on epsilon plus and minus in this way.
And then finally the bracket with a certain minus, is that the q minus analog of the number?
This one? No, this is a representation of the normal spin SU2 representation with higher spin m minus. So think about it as spin 3/2 or something. I mean, it also runs over this m minus here. As I should actually, so it also runs over the m minus. And then you compare it with the m minus representation on this side, and then you get this ng in terms of the m plus m minus.
But that's not a rewriting of the previous formula.
No, it's not a rewriting. It's just a definition of what invariants that have been mathematically defined have to do with the invariants that I'm now defining, or physically defining. Yes?
I saw the relation between Goba, Waba, and the double weakness is still genus by genus expansion.
Yeah.
But the relation between those chief theoretical invariant like ET or
Mhm.
ET, you actually have the sum of the genus.
That's true. I mean, I'm saying that only the full. I mean, you need the full genus information, so to say, in order to recover it. So I'm not saying that that you can. Well, I mean, this is sort of there's an equivalence, or that. I mean, the full information is equivalent. Let's put it like this: equivalent information. But you need indeed also make a reorganization in terms of the genus in order to do it. So, well, I mean, in some sense, this is physically very, very sort of say clear. So the BPS states they are they are characterized, well, they are specified by their charge. The charge is easy to convert in a mathematical language. This is just beta element. So this is a beta in H2 of x over the integers. Then there is the mass. The mass is actually also easy to say. If you take a curve in the class beta and you and if you integrate your symplectic form over this gives the mass. This is in the A model. And then also we need it in the B model. There you have a 3 cycle which is associated by mirror symmetry to this curve class, and then you integrate the 3-0 form. This is for the B model. And then, yeah, now in physics terms, it's easy to say we have, of course, then the spin in S U2 plus minus. And in some sense, if we look only at the Gromov-Witten invariant, we throw away the spin information in this plus spin information by summing over it. So we throw it away, and then and that gives us, so to say, I mean, not doing that gives us the refined invariance. So there's actually one remark which I also should maybe I can still do it. You can stop it, right? Okay. So so if you look at this redefinition here, and you compare it with this definition, then you can see that if this definition is true, so this is actually symmetric in epsilon 1, epsilon 2 goes to minus epsilon 1, minus epsilon 2. And that means actually that that if this interpretation is correct, then that the f k half g should be 0 if k is odd, because otherwise this expression doesn't enjoy the symmetry if this is not an even number, and therefore this should be 0. And in fact, this has raised some questions in the literature, because in Nekrasov's partition function with masses, this is not the case. But if you refine Nekrasov masses, ME to ME plus epsilon 1 plus epsilon 2 over 2, then this is true in Nekrasov's partition functions, in Nekrasov's partition function. This is true. Well, I mean, this is just a remark. So this is compatible. If you do this in Nekrasov partition function, then you have also the symmetries. But if you don't do this definition of the masses in Nekrasov partition function, it does not have this symmetry. And well, I mean, also to give you some recent paper on omega background where you can find all the definitions, I would suggest you to read Nakahama and Oguri and the references therein. So this is archive. This is just the, I mean, it's a very active field. I'll just give you the last paper on this. This would be 110655 O3. And maybe the most mathematical paper of this, which I cited there, is Nekrasov and Witten, where they discuss the generalized omega background, unfortunately, on something like 150 pages. So it's a big subject these days in physics. So the second part of my talk will be merely to calculate, actually, these FGs. So these quantities I want to calculate, and I want to calculate them in the B model. And in getting to this calculation, or setting up this calculation, we will find a generalized holomorphic anomaly equation, hence the second part of my title, and this is the main result, maybe, and then the way of using it in order to calculate the FGs. So this was done in collaboration with Mingxing Huang and Amir Kashani-Pur, and the paper with Mingxing Huang was from last fall, or last late summer, and the paper with Amir is about to coming out. So when you have calculated them in the B model and used the mirror map and so on, then you can make contact with this generalized invariance, and for instance, for geometries like O minus 3 over P2 and similar non-compact Calabi-Yau. I should stress that this all works only for non-compact Calabi-Yau, because, as we said, we need this isometry, and compact Calabi-Yau have no isometry. So that also should be noted, that this invariance can only be defined if X is a non-compact Calabi-Yau and has this isometry.
As a sum of more refined invariance?
Yeah, in some sense, I mean, I think, and Dennis Aru had some comments on it. I mean, if the Calabi-Yau manifold would have another vector field, that means a continuous U1 symmetry, then maybe it is related to something which has already appeared in literature, but I'm not completely sure. I mean, if so, only if this, you have this additional isometry, maybe you can define in the world of Gromov-Witten series something like, yeah, something like this. So the rest of the talk is basically calculation of f n g, and now I don't. They have to be integers, so by this remark, this n, so I don't have use this k half anymore, and by in the B model. B model using the generalized holomorphic anomaly equation. And that is together with Mingxing Huang. This is 2010, and then plus Amir Kashani-Pur. To appear. So in the B model, I mean, I have to remind you of some notations in the B model. So if you have this f not g, then you can define it as an integral over the moduli space with a certain measure. So this the B model is basically, in the B model you map a Riemann surface eventually with punctures to a point in X in the mirror, and accordingly these FGs are essentially defined over the moduli space over this Riemann surface. So you need to provide a measure of dimension 3g minus 3, and that can be done by the following expression. So this is contracted with coordinates on the moduli space, and then gives a measure. And this b k, they are basically integrals of g minus mu k, where mu k is a basis of Beltrami differential. So mu k is in H 1 sigma g t sigma g. And then the g minus, there are basically 4 of them. So we have g minus generate the 2,2 worldsheet supersymmetry. So that is the setup. And as we probably know, from the work of BCOV, this is evaluated with a particular action, and if you perturb this action, so if this is an action which can be made dependent on t and t bar, so it's first an holomorphic action, but then you can perturb this action by a t bar O2 d 2z, so it's a two-dimensional action. You need a this is a two-form operator already, so you can perturb it by such an operator. And then if you take the derivative with respect to, let's say, tk bar fg, so this has also in principle has an index k, and this has also an index k, then you get the holomorphic anomaly equation k d I, let's call this j, d k f. Well, we can also always call this already like this, because as I said, this is the normal genus expansion. Then we have m h, oh no, sorry, we have just h, and then it is d I f h dj dk f g minus, where this runs from 1 to g minus 1. So this is the normal holomorphic anomaly equation. This is the BCOV holomorphic anomaly equation. And what we now suggest is that actually our proposal is that these things are defined by insertions to this B model. So when we want to have this, then we basically make an integral over the same integral with an insertion of a certain operator, and then the same integral like there, bk. So it's just an insertion. There's actually k and k bar here. So this should be the definition of this quantity, and this is actually for g greater than 1, and for g greater than 0, and for and then f0g. We just assume that this is the correlation function. This has no moduli space, so it's the correlation function of phi 0, phi 1, phi infinity, where, and then on, where this the relation between phi and O is by this descent equation. So if you make such a proposal, then you can say, okay, the epsilon 1 plus epsilon 2 squared is basically S, and it's just the deformation direction. And now you can write the holomorphic anomaly equation, the generalized holomorphic anomaly equation. So from there follows the generalized holomorphic anomaly equation. Yeah.
So what is H? This operator you said there, H, what is it?
This is just n. So this is an n-fold insertion of operator. Yeah, exactly. So that's also the. So it's important that that actually n was even, because otherwise, I mean, yeah. So otherwise, I cannot define this way things for half integers because I cannot insert half an operator.
The notation f is just equal over minus just integration f 0 g is integration over n g bar. And
So mg bar is the moduli space of Riemann surfaces.
yeah, and then you said it's related to this action and we can
Yeah, this correlator is evaluated with this action, and you can perturb it.
what does the how does the t and t bar compare with what's the coming with t and t bar?
Well, it turns out that this correlator is a correlator in an action which depends itself on t and t bar. So you have a conformal field theory which you can perturb by t and even by t bar, and so the correlator of the conformal field theory can depend on t and t bar.
And the t and t bar does not show up in this.
They don't show up in this expression only via s. That's relatively tricky
Okay.
dependence.
So that bracket is sort of evaluated
With this action,
differential action.
yes, and in this action you have actually a dependence on t and t bar. So the t dependence, I agree on this in this equation, is just hidden in this correlator.
That
Yeah, this is a covariant derivative with respect to the Weil-Petersen metric on the moduli space of the Calabi-Yau.
So should you, this is basically the B model passing the
Yes.
You integrate out the normal direction, you should localize an n bar on constant map. Well, constant map is ng bar cross x. It's not just ng bar.
Yeah. You mean mg bar
Yeah,
cross?
it's cross the target, right? Because that's the points where it maps into.
That's right. Okay.
Where's the factor?
This is again here.
Yeah, you already also integrate on
Yeah.
the target.
Okay. But this is easier even. Yeah. So this is for g equals 0. And sorry, this is sorry. This is for n. Actually, this is for n plus 1 and 0. So this is the g. So then, what is the, you can follow from that the generalized holomorphic anomaly equation would be t chi bar f ng, and that is now similar in many respects. So it's j k k bar, and then the first factor doesn't change at all. F n g minus 1. And the second and then you have a derivative with respect to mh, and then a derivative with respect to n minus m and g minus h. And here's a prime, so for instance, so this means you don't sum over 0, 0 is excluded. And also mg is excluded. Both of them are excluded in the sum. Sum of the highest and the lowest. And that is actually the most important equation. So this is the generalized holomorphic anomaly equation by which Dij is going to be the Weil-Petersen metric on the modular space. And now these are the equations that I want to solve. And it was asked already, so let's give them nice names. So these are my equations, A and B. And what we want to do is we want to solve now A and B. These are recursive relations, and I want to give you a procedure how to solve them. And let me make a couple of remarks. So, A, B are recursive. And G. And so we actually solve them. Then this derivative di is the derivative with respect. So this is the so this is the Weil-Petersen metric connection. And then the C, this C I J K also follows from special geometry. So this is basically C J bar A bar I bar. Also comes from the metric, and here is also a factor of the Kähler potential. But the point is that all this information is determined at genus 0. And now, in which geometries can I? Yes?
So you have the same propagator, basically, right?
I have the same propagator. When you look in the, when you know BCU, then you have the same propagator to solve it. That's correct. And therefore, the structure of this, the answer is very similar. So the structure of the answer is similar. So this actually work? Ah, okay. So, okay. I don't know what to do because this. Okay, so then, I mean, otherwise I keep slapping on it. So let me now, in the remaining 15 minutes, also try to explain you how to solve this. This recursive relation, and as Yongbin anticipated, it's not so different from the solution of the normal holomorphic anomaly equation. For instance, the same non-holomorphic object terms shows up, and therefore this method of direct integration that we developed actually is applicable to this case. So it remains to solve this holomorphic anomaly equation, and this is based on two considerations. One is modularity, and the others are boundary conditions. So modularity fixes almost everything, and then there are certain boundary conditions that I have to impose. And so if I give you the modular properties and the boundary conditions, then you can actually solve this recursive equation. So the last topic is the extension of the direct integration method direct integration method. To the generalized holomorphic anomaly equation. Holomorphic anomaly equation. So the so this is the following data that you need. So you need the data that you start with are as follows. So you have a family of Riemann surfaces. Let's call them C, G, tilde, and the genus has to be greater than 0. So this works, and this G tilde has nothing to do with the genus before. It's just a genus of this Riemann surface is parametered by U, which are the B model parameters, which are as many as the P's. And then, while you can assume, for instance, for simplicity, that it's hypergeometrically given. And then there is another data, so a meromorphic differential. And that is called lambda. And you have the property that if you take dui of lambda, then you get the meromorphic differential. So you get I minus 1 dx over y in case of this Riemann surface plus probably an exact piece. Plus exact. So these are the data that you need. And in addition, you have often residuum. If x goes to xi, then you have residuum of this m, which you call mi. These are basically the masses that appeared also before. These are the masses. These are the additional parameters in this problem. And then you have the periods, t, I, which are then the integrals over the meromorphic differential over the A cycle, and the t, di, which are the integrals over the meromorphic form over the B cycles, where A and B form a symplectic basis on this Riemann surface. So it turns out that this sort of data allows to apply the formalism. The formalism can be applied to well, first Seiberg-Witten theory, and then CG is the Seiberg-Witten curve, and lambda is the Seiberg-Witten differential. I mean, they have invented that, so that's maybe the example. And then it can be also applied to matrix models. Then CG is the spectral curve, and lambda measures the Filling fraction, so it's this differential which measures the Filling fractions. And then finally, it can be applied to topological string. Then CG is the mirror geometry h, x, y equals 0 that you know by Fourier construction. So the mirror geometry is basically given by this equation. So that is x hat, the mirror geometry to this non-compact Calabi-Yau manifolds. And in this case, the differential is something like log x dy over y. And these are the two sort of set of data where it can be applied. So here in the matrix model, actually the polynomial that is polynomial potential. We have to this polynomial potential. Otherwise, we don't know how to do this. So then I will discuss a little bit of the data for G tilde equal 1, because it's just simplest for illustration. Okay, so then we have, let's say, the curve is given in the Weierstrass form. So it's like G2 of U of x, there's just one U parameter, and G3 U. And now I cannot give you immediately what the A period is, but I can give you by this property what this differential of the A period, the T period is, but I can give you the differential of the T period with respect to U. So he has only one T, and if I take a derivative to U, then because of this equation, it's just the holomorphic differential, and that can be written for the Weierstrass form up to a normalization as G2 over G3, and then E6 over E4. So that is a neat way of writing this differential. And then you have, of course, the J function. The J function is like E43 minus G minus E6 to the 2, and this is also for this particular family would be G2 to the 3, G2 to the 3 minus 27, G3 to the 2, and this is the discriminant of the curve, which also depends on U. Now this data already makes it completely easy to write down the F00, so the genus 0 sector. So the G equals 0 sector is now already defined because we have that tau, which is the argument of this of the J function. This is by definition d F00 over d T, and we know what T is by just integrating this equation, and we know what tau is by inverting the J function in terms of U. So we certainly know already what F00 is, and we also know the metric with respect to which we have our covariant derivative. So this is just 4p over some C naught tau 2. That is just the metric on the upper half plane. And we also know what this 3-point coupling is. The 3-point coupling is just the tau over dt. Well, this is also can be written as the third derivative of this prepotential with respect to t. So that we know all the genus 0 data already, and then the genus 1 sector, I can now have to start to write down the holomorphic anomaly equation, to solve the holomorphic anomaly equation. And in the genus 1 sector is a little bit different because the holomorphic anomaly equation for genus 1 is a little bit different than in the general case. But this can be easily obtained once you see this data and impose some physical boundary conditions. So now we have to solve basically this holomorphic anomaly equation to get F1, but we should also notice, this I just erased, if n is if n is 1 and g is 0, then this object is still holomorphic. That just means that's just because you don't have any parameters for a 3-point function on the sphere, which this is, and therefore it's still holomorphic. So so we get the n plus g equal 1 sector. So we have now this double index, and there we have F 10 is actually 1 over 24 log of delta. I mean, this has to be argued from the boundary condition essentially, and I'll explain you a little bit how to do this. And then from this equation here, this equation B, we can integrate F01, and it turns out to be something like, you can write it in this quantity I given you. So it is log of g t bar delta over 1/3. So notice that this is already non-holomorphic. This is still holomorphic. This is non-holomorphic. And it can be also, well, it's essentially determined by up to some ambiguity. And this ambiguity, so if you take t to infinity, then you get a holomorphic limit. And then you get the t, t du, yeah, minus 1 over 12 log of delta. So now I have to tell you basically how you get holomorphic pieces. So this piece is actually determined by the holomorphic anomaly equation, this piece. But these pieces, they come from the boundary conditions. So I have to say a little bit about the boundary conditions. And that's actually very nice. So what I claim is that I know how all the FGs behave at the zeros of the discriminant of the Riemann surface. I know at least the leading behavior at the zeros of the discriminant. And this actually provides enough boundary conditions to solve the problem. So the boundary conditions are as follows. What are the boundary conditions? So let's suppose that for u equal u naught, there's 0, so it's the 0 of this discriminant and the curve degenerates. Then I also know that the TD cycle with this lambda over b, actually goes to 0. So this is just the nodal singularity of this curve. And now I know that this corresponds to the mass of a BPS state, so I can actually evaluate the F S GS TD. This is about this calculation that gives me the boundary condition. So it's the integral x over dx from 0 to infinity, and then it's x minus x TD. This is the mass, and then it's the Stringer loop calculation. That is an analog of the Gopher-Kummer-Waffer calculation for this case, so that I explain not very much in detail. It's not so complicated to understand this. So this gives you a general boundary properties if this TD goes to 0. So you expand this for TT goes to 0, and you find that it goes like minus 1 over 12 plus 1 over 24 S GS minus 1 log 80. So from this boundary condition, now you can compare this with that. So this condition is the one which corresponds to F1 0. And this is the reason we have here this 1 over 12 delta. Goes with discriminant, so 80 goes like u minus u naught in the leading order, and degenerates, and so on. So this goes like S 7 over 5. So these are all individual Bernoulli numbers that follows by doing this integral. And yeah, so we get something like and if you do this systematically and leading to if, then you see that constant which depends on n and g, basically this Bernoulli number, and then t d to the power 2g plus n minus 2, and then there is a so-called gap, and then it goes only this order a td 0. So these are the boundary conditions, and now you can use. I mean now. The story I just brought it up. The story is now that you can introduce x, which is an e2 hat, g e6 over sorry. Show now that f and g, the solution to the recursion relation is basically something like that this is given by so it's given by 2 n plus g minus 2, and then k equals 0 to 2g plus 2n minus 3 xk. It's just the polynomial in terms of u. So that's the result of the recursion relation. And now you see, since x is the only unholomorphic quantity in this game, and its derivative with respect to t bar that makes the holomorphic anomaly equation can be replaced by a derivative with respect to e hat. And that's the reason that at the end I know already what the highest power of e hat in such an expression is. Because on the right hand side you get by the derivatives 2 more powers of e hat, and then you integrate once. So in every step it actually, the genus grows by 3. And so I know this behavior. And I also know from the holomorphic anomaly equation what are this pk of u except for the k equals 0, where there is no x hat, because this is an integration constant of the holomorphic anomaly equation. I mean, normally I convert the derivative t bar with respect to e hat, and then the only thing that has no e hat is this p0, and this turns out that this boundary conditions are sufficient to fix the polynomial u. Because the polynomial u can also not be too high, because you want to have this expression regular when u goes to infinity, and the u power of the discriminant is of course bounded by as many zeros you have. And as many zeros you have, as many boundary conditions you get. And therefore you can always determine this k of u, and then you can convert this to the A model and get this generalized background. So now do I have checks? Yeah, I have checks. If I apply this to the Seibert-Witten theory, then I get Nekrasov's partition function after making this shift in the M. If I do to the topological string, let's say to the geometry O minus 3 over P2, then I know, of course, what this H is. We have worked this out and can do this formalism and then get something which is integer but also coincides with the generalized topological vertex, which in this case you can apply. So there was a formalism by Iqbal, Houri, and Wafa generalizing polymorphic vertex. And this works for some of the historic geometries, and therefore also this Danish one, relatively sure that my procedure works. What I'm not so sure about is what these numbers are that I can nicely reformulate in terms of this modular functions. But I don't know what. I mean, the challenge maybe for you is to give to it an interpretation in terms of geometry on this Calabi-Yau manifold.
Any questions? Oh, this remark. Context. There's also another parameter, that's for access for the open.
That's for the open environment.
But it's